Hi everyone. Today we're going to be talking about 15.2, which is double integrals over general regions. The last thing that we did before break was we looked at double integrals over rectangular regions, where we only had constants in our bounds of integration. And this lecture is going to be a little different because we've got now non-rectangular regions. And what that means is that our double integrals are going to have some functions in these boundaries. So there's going to be a few more decisions that we need to make, and we won't be able to use Fubini's theorem. So remember, Fubini's theorem said that you could just switch the numbers in the two bounds of the double integral, but we won't be able to do that. We kind of have to go through a slightly longer process. So I've got an example here of a region, and this region is bounded between this curve, y equals square root of 1 minus x, and then in your book this might be written as, x is greater than 0, y is greater than 0, so that we're talking about this region in here. The first thing I want to do is, if you're given the sketch already, is to figure out what x and y are in between. One first attempt at this might be to say that x is in between 0 and 1, which is true, and y is in between 0 and 1, which is also true. But just because these are both true, just like when we were setting up the domain of a function, we only want to talk about this region underneath the curve right here. And if all we're saying is that x is in between 0 and 1 and y is in between 0 and 1, then we're actually just defining this rectangle. And that's not what we want. We want to kind of cut this little region out of the rectangle. So this is not going to be valid. So this is not valid. What would be better is if we could say that y is in between 0, that's fine. Here's the curve, y equals 0 down here, and the top curve is 1 minus x. So that kind of keeps us bounded between these two curves. The curve y equals square root of 1 minus x, and then the curve y equals 0. And then we can say that x is in between 0 and 1, and then this is going to define the region. So this is what we want to do. We don't want to define rectangles when we really want to talk about this region here. Okay. So now that we've got this, we really have two options here for how we want to write our double integral. So we'll kind of write them down here, and maybe we can develop an intuition for which one's going to be better. So the first one is going to be dx dy. The other one's going to be dy dx. And both of these, remember, I'm only looking at the region here. So both of these are going to have some surface that they're finding the volume of. So the volume underneath that surface. Over here on the left, we can say, let's see, x is in between 0 and 1, and y associated with this integral is between 0 and square root of 1 minus x. Over on the right, same thing, y is in between 0 and square root of 1 minus x. X is in between 0 and 1. And only one of these is going to end up being valid. So I want you to think about what this is going to produce when you actually solve this integral. So we saw how to solve some double integrals. Um, at the end of solving this one, for example, we'll have some functions of x. We'll evaluate that at square root of 1 minus x and 0. And then at the end, we'll evaluate that function of x between 0 and 1. So this one is going to produce a constant. But when I look over at this one, I'll do this interior integral first with respect to x. And then what I'm going to be left with when I evaluate this y integral is some function. So this is going to produce this produces a function of x when we solve the total integral. And we know that this is the correct one because what we're finding, remember that these double integrals represent the volume under a surface. All right, so we have some region, and then we take the volume under this surface, and that's what this double integral is equal to. So if it's a volume, it needs to be equal to a constant. We want to be able to say it's 100 units cubed. So this is the one that we want. And we can't have something that produces a function. So in general, the rule that we have is that if we have constants on the outside here, that's good. But if we have functions on this outside integral, then that's not going to produce a constant, so we can't have that. So we'll go ahead and write that down. In general, so I'm going to be very general about this, and I won't even call them x and y. I'll just call them w and p. All right, to say it really doesn't matter what. It's not always going to be dy dx or dx dy. Just whatever order produces having functions. On the interior integral, and we want to have constants on the outside. So that's going to be true for double integrals. That's going to be true for triple integrals. We always want to have these constants on the outside, or on the outside integral. Okay. So I want to look at an example, something that you might see in the book. So let's say that you're given this f of x and y is equal to x to the third times ey to the third. And I'll tell you that 0 is in between, or sorry, x is in between 0 and 3, and y is going to be in between x squared and 9. So I'm going to set up this double integral. I've got the double integral. Here's my surface. And then thinking about trying to get these functions on the interior integral and constants on the outside integral. I want to have dy for the interior integral, dx for the exterior integral. So this will be from 0 to 3. This will be from x squared to 9. So we're definitely following the rule that we have our constants on the outside, and this seems good until we try to actually solve this double integral. So thinking back to what we did with rectangular regions, one of the things we might have to do is switch the order of these if this integral is too difficult to do by itself. So um, if we tried to integrate this with respect to y, we might want to try some u substitution. So u would be y to the third, and then du would be 3y squared dy. But we run into that same problem that we saw with our rectangular regions where we don't have a 3y squared dy anywhere in here. So this is going to be an impossible integral to try and do as it stands. So what we need to do is, so I'll say not possible to integrate. We need to change the order. Okay. So since it's not possible to integrate this and we're trying to switch the order, the first thing I want to point out is that we can't do what we did with rectangular regions where we just take the 9 and the x squared and move it over here and the 0 and the 3 and move it over here. First reason is it's not a rectangular region. We can't do that, right? So we can't use Fubini's theorem. We also can't do that because we would have an x squared over here, and we'd run into the same problem we saw above where we have functions on the outside. So we want constants on the outside there. So in order to change the order of this, I'm going to draw a sketch. I really highly recommend. I'm going to do more than recommend this. I think this is really the only way to consistently get your region right is to draw a sketch of what's going on. So I'm going to try and sketch this region. So x is in between 0 and 3. So this is the line x equals 0. This is the line x equals 3. So I'm going to be in between these two lines, and then y is in between 9. So here's 9, and then y equals x squared. So I've got some regions here, and we want to think about which of these two regions we're talking about here. So x is in between 0 and 3, and y looks like x squared is on the bottom and 9 is on the top. So this is the region that we're talking about up here. And our goal for this is to figure out, since we want to integrate with respect to x first, we want to figure out how to describe this region in terms of x as a function of y, and then y is in between some constants here. So based on this sketch, again, it's going to be really difficult to try and figure this out without this sketch, but if I want to talk about the bounds for y, I know that I want that to be between two constants when I change the order. So y is in between 0 and 9. And then for my x, I want to say that x is in between this line and this curve here. So x has a lower bound of 0, and then the upper bound for x is going to be this curve here. So right now what I have is that y is equal to x squared. So you can probably see that I can rewrite this. If I'm talking about just the right-hand part of this curve, I can say that x is equal to square root of y. Okay. So y is in between 0 and 9, x is going to be in between this curve, x equals 0, and this curve, x equals positive square root of y. So based on that, we can rewrite this as, I guess I'll save that. So this same function now when we write this in terms of dx and dy, x is in between 0 and square root of y, and y is going to be in between 0 and 9. Now we're looking at something that hopefully we can integrate it in this order. Something else that I want to point out is that I really needed this sketch in order to figure out these bounds for it. If you just try to do algebra in the bounds here, you might end up with something that looks a little bit different, like trying to switch this over and then maybe call this, well, x squared is sort of like square root of y. Basically, you're just not going to be able to do that. It's really tempting to try and do algebra in here, but the sketch is really crucial. So make sure you're drawing the sketch if you need to change the order. But let's try to solve this one here. So this one, I'm going to go ahead and pull this out to the side here, and I want to integrate this with respect to x. I'm going to get 3x squared, where x is equal to 0 or square root of y. Oh, sorry, I'm integrating. Sorry about that. 1/4 x to the fourth. And then at the end, I can integrate that with respect to y. Okay. E to the y to the third, and this is going to be 1/4. And that looks like y squared. All right, square root of y to the fourth dy. Now I'm looking at just a nice calculus 2 problem, so I'll put that 1/4 out in front there. So I sort of fixed the problem that I had earlier where if I want to do a u substitution, I needed a 3y squared term, and here it is. Here's that y squared term. So we'll say now we can do u substitution. Okay. For the next one, I want to talk about another decision that you can make, but just in summary here, what we did was we tried our best based on the information to make sure that the constants were on the outside, functions were on the inside integral. But in this case, we need to change the order. We did that by drawing a sketch of the region and figuring out some new bounds for x and y. I'll go ahead and finish this problem up. just so you see that it actually does produce a number here. So I'm going to say that u is equal to y to the third, du is equal to 3y squared dy, so that means that 1/3 du is equal to what I've got here, y squared dy. So from above here, I've got 1 over, I'll take that 1/3 and call this 1/12 from 0 to, and remember I'm no longer integrating with respect to y, I'm integrating with respect to u. So I'll end up with not 9, but 9 to the third e to the u du. That 1/3 is already taken care of over here. And that is going to be equal to 1/12 times e to the, well, integrating this is just going to be e to the u, so this will be e to the, whatever 9 to the third is, minus e to the 0, which is just 1. So constant, 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 constant. This is going to produce a number here. So this is our volume under the surface. Okay. One more example to just kind of show you another decision that you might have to make. This is going to be similar to the first one, where we are looking at this region, or rather this curve. So I'll have the same curve, y equals square root of 1 minus x. But here I'm going to talk about a region that stops at, let's say, 3/4. Right, so I'm only talking about this region here. If you think back to Calculus 2, you did some kind of double integral style things, or you were looking at functions that were bounded between two curves. And one of the decisions that you had to make was, is this a dx type of problem or a dy type of problem? Which of those two is going to make this problem easier? So if I want to kind of draw around in here, the easiest way to represent this is to say that y is in between 0 and square root of 1 minus x, and that x is in between 0 and 3/4. But if you think about integrating this with respect to y first, we're sort of going to run into an issue because dy looks like this. Right? dy is just a small, infinitely thin rectangle that's got dimensions dy. So this is our dy, and that's going to be in between 0 and 3/4, 0 and 3/4, 0 and 3/4. But the problem lies up here, where we sort of have to split this into two integrals, right? Because we've really got two regions here if we're thinking about this in terms of dy, where one of them says it's bounded in between 0 and 3/4, 0 and 3/4, 0 and 3/4, right up until this point. Now we're in between 0 and this curve. All right. So if we can avoid splitting this up into multiple integrals, we definitely want to do that. So let's see if dx is any better. Spoiler, it is. Right? So if we look at dx, this is going to be consistent throughout the entire region. So it's always in between, y is in between 0 and square root of 1 minus x, 0, square root of 1 minus x, 0, square root of 1 minus x. And that's going to be true all the way across the region. So because that's, this is sort of our, right, this is our dx, these are our dy's, is that we want to integrate this with respect to y first. Right, so we have y is in between 0 and square root of 1 minus x, and x is in between 0 and 3/4. So if I set up my integral, sorry, and x is in between 0 and 3/4, then this is already in the correct form that it needs to be in. So this is a properly set up double integral. And we don't need to change the order. This was the correct order to work with. One thing I want to point out about this process is if we need to switch the order, or if we're drawing this sketch to switch the order, or if we're trying to figure out the bounds of this, I want you to note that all of this work is only to figure out the bounds. Right, so this whole process is just figuring out what numbers go here, what numbers go here, what numbers go here, what numbers go here. If we sorry, if we kind of think about the order that we're doing things in, the first piece is figuring out what goes into these double integrals. That was all this work that we did. And then the very last step, notice that we didn't have to use this surface at all. So the very last thing that we do is going to be looking at this surface, f of x and y. So looking at the previous example up here, we kind of did all of our switching, all of our boundary work first. Then we started to actually tackle this integral. So we changed the order. This stayed the same the entire time. Then if we actually ask you to solve it, then you'll need to work with that boundary function. But oftentimes, especially with triple integrals, what I'll ask you to do instead of solving for this volume under the surface, what I'm going to ask you to do is just set up the integral, and this is all I'm asking for. All right, so if I ask you to set up a double integral that represents the volume under the surface z equals f of x and y over this region, this is where you can stop right here. So that's it for this video. And the next video is going to be about polar coordinates. So we'll start to work with regions. So this was not quite a quarter circle, but we can kind of significantly make this significantly easier if we're talking about a quarter circle or some kind of like half circular region. We'll be able to convert that to polar coordinates, and that'll be section 15.3. All right, see you then.